All right, hello everyone. Today we're very excited to have Joe Felsenstein on the Phyloseminar. This is actually the first talk in a three-part series on macroevolution and phylogenetics. Next, Luke Harmon will be speaking on Thursday, February 24th at 9 in the morning, our time, Pacific Standard Time. And then Brian O'Meara will be giving a talk on Wednesday, March 16th. So before I start, I see there's a lot of new people here. Welcome. We do encourage questions during the talk. And if you have one, you can do one of two things. If you've already debugged your audio, just type in to me or in the message box, just type in that you have a question, and then I can turn on your audio. And you can ask the question, or maybe easier is just to type in the question into the message box, and then I can ask it. So speaking of the message box, let's just go ahead and warm it up. So for the next series of talks, I'd like to have some software demonstrations. So if there's a software demonstration that you'd like to see as part of Phyloseminar, just type the name of that software package into the message box. So now on to our talk after a very brief introduction. So a friend of mine actually once said that not every field has a godfather, but likelihood-based phylogenetics certainly does. So I'd say that Joe is that godfather, and he was there. He wasn't just there at the beginnings of the field. He kind of was the beginning of the field, and he's developed much of the original mathematical, statistical, and computer science machinery, which is now standard. And his contributions have really ranged all the way from the theoretical to the practical. So recently he, of course, wrote a book on phylogenetics. I guess it wasn't so recently, but it's a great book, and I'm sure many of you own that book. And we're very lucky to have him today. So take it away, Joe.
Okay, before we start, Fred, could you pop over? I managed to click on the wrong box over on the left screen, and now I can't see any of the windows, but I'm sure I'm broadcasting. If you can come by and restore those windows, that would help me for a moment. Well, this is going to be one of those talks in which somebody talks about, I tried to look at these guys, and then that caused this window to complete. Okay, so I'm on live now.
Yeah.
I don't hear myself in the earphones.
That's a good thing.
Okay. Okay, usual glitches. This is going to be one of those talks in which somebody comes along and tells you about three things they did recently and spins one of those contexts in which they try to make it out to be the essential task for modern science. And I've heard a lot of those. And now I'm giving ones like that. And of course, the audience has to be very skeptical and say, look, this is just three recent projects from this guy's lab. Forget about the context. But I actually think there is a context for this. When I finished writing my book in 2003, I really had to decide what I was going to work on next. And there were simply too many good people working on the statistical molecular phylogenetics. And besides which, I'm not a molecular biologist. I'm trained as a population biologist, a theoretical population geneticist originally. And I used to be head for 5 years of the computational molecular biology program at our university. And I used to complain to them and say, look, you've got the head of your computational molecular biology program who doesn't know the names of all 20 amino acids. And their answer to that was, look, it's fine. As long as you fill out the forms, we don't care that you don't know the names of all 20 amino acids. But I felt that since I didn't know the names of all 20 amino acids, I really should not spend my time working on things molecular, because I have no really good feel for them. On the other hand, I do have some background in quantitative genetics. It was my original subject of my postdoc in Edinburgh under Alan Robertson. I think I've got some training there. And there were really interesting things to be done. And over the years, I've tried to talk about connections between things like quantitative genetics at a within species level and models that people try to make of non-molecular traits, particularly morphological traits, but it could also include behavioral traits, across phylogenies. Most people who work on non-molecular, particularly morphological traits, do so using parsimony methods. And some of them do that for ideological reasons, thinking that parsimony is somehow superior to all possible methods. But a lot of people simply do it because there aren't very many good alternatives. However, over the years, there has developed the use of statistical machinery involving Brownian motion, coming from the work of Edwards and Cavalli-Sforza in 1964. And I did some stuff on this in my thesis which I wrote in 1967 and published in parts of it in 1973 and 1981. And over the years, I've been talking about the use of Brownian motion models and trying to talk about how that relates to quantitative genetics. And that's what I'm going to use as my underlying theme here. And the connection connection involves some concepts which people are not very familiar with. And over the years, I've been hammering away, trying to mention in papers in 73 and 81 and 88 and in my book that, in fact, where does covariation among traits across a phylogeny come from? And I'll be getting more to this a little bit later. Some of the traits that people are using for morphological characters are being analyzed these days by morphometric methods. And so the first third or so of what I'll talk about is a project that's a joint project with Fred Bookstein. Fred is now part-time at the University of Vienna and part-time at the University of Washington, although for many years, of course, people think of him as being at the University of Michigan. So here is, is this supposed to work? Let me get the mouse in the right place here. There is the mouse, okay. I'm trying to advance the slides. Click on the
click on the, if you click on the slide.
There we go. Thank you. So there's a picture of Fred, and this is going to be about the issue of how do we take data that's analyzed by the morphometric methods that the morphometricians under the leadership of Fred for the last really 20 years or 30 years almost have been developing. And there's some very interesting details there. Fred and I have a grant together, and we've been working on this, and so this will give a quick summary of what I've discovered and been able to have him agree with, I hope. One of the things you can do is that you take the coordinates that you get out of morphometrics. And in morphometrics, what you do is you take your specimen. Let's imagine it's a two-dimensional specimen, say a fish, a flat fish. And you have a digitizer. And you take the fish and you throw it down on the digitizer, and then you go around and you digitize landmarks. Or you have an image capture with a camera, and a computer somehow gets your landmarks. That would be a more sophisticated way. And you can take the coordinates of the landmarks, which are here a set of two-dimensional data, so they're a set of pairs x1, y1, x2, y2, up through xp, yp, they're p landmarks. And you could just say, well, look, if we want to model these changing across a phylogeny, let's model them as Brownian motion with covariation among traits and unequal variances of change. All of that is allowed in the Brownian motion model. All of that is a standard part of comparative method studies these days. And what we're going to do is talk about what you do if you have a phylogeny provided by molecular data. And let's assume for the moment that the phylogeny is error-free, although we can come back to that. And what you want to do is know about the covariation among the traits. You're working in a comparative methods mode. I think largely we're going to be seeing that done rather than trying to use the morphometric data to infer the phylogeny. And the reason simply is that there's so much more molecular data that it's going to be almost a waste of time to use the morphometric data. There's some arguments for doing it. Excuse me. Excuse me, I have a remnants of a cold. So, okay, we take these. Can we just take these 2p morphometric coordinates and just go use them? Well, the answer is you really can't, and you can't for a couple of reasons. One of which is that when you took the fish and flopped it down on the digitizer pad, you did so, but you just threw it in a random place. The placement, the location is actually not data. It's not data about the fish. So you want to somehow get rid of that. Furthermore, when you flopped it down, you probably rotated it a little bit without thinking about it. So you want to somehow correct for that rotation. And I'm going to assume here we're interested in both size and shape, although much morphometric work is done removing size. I'm not going to remove size. But we want to remove these meaningless rotations and translations from the specimen. Now, one way of thinking about that is to say, well, what we're trying to do is take all of our specimens and superpose them properly. And that's a very tempting thing to do. And when we started this project, that's what I kept saying to Fred. We've got to find the great superposition method. And Fred kept saying to me, no, there is no way to superimpose them. The data is simply not there. You can't superpose them. And I said, no, it's pretty obvious. There's some way of superposing. We've heard about Procrustes fitting and things like that. Let's figure out what's the right way. Well, Fred kept arguing with me, and the arguments got quite heated between us, and we really were upset with each other. And finally, I realized that he was absolutely right, that I was trying to do the impossible. One of the reasons I'll try to explain it is that if you were to consider specimens properly superposed, you will begin to see after a while that the location of information is not there. And I think the best thing for me to do is actually go ahead one slide and consider a specimen, an imaginary specimen. So here we've got an imaginary fish that has 13 landmarks. They're the corners here. And we imagine a lineage in which this fish is changing. The shape of the fish is changing. Uh-oh. Somebody went ahead. I touched the mouse, and that was a mistake. Here we are again. Let's see what happens here. So here is the fish. Here's a lineage. The fish is changing in the lineage. The last 4 landmarks are going backwards. So the front 9 landmarks are completely superposed in this lineage, correctly superposed. Here is the correct superposition. There is the change in shape. You went from this shape up to that. Over here on the right side is another lineage, starting with the same specimen, the same original form. And in this one, there's something different that's happened. We get a different superposition. The last 4 landmarks are completely correctly superposed. The first 9 have moved forward by the same amount. I should have said on the left specimen, things move backwards 1 centimeter. On the right, all 9 move forward 1 centimeter. Now, you might say, gee, those are 2 different situations, aren't they? They have different superpositions. A moment's consideration of those forms will show that they are exactly the same form. And I can guarantee you they're exactly the same form because when I drew them for this slide, I simply took this form in the upper left and copied it over, and it is the form in the upper right. I just put it down in a different place. So then you can immediately see that in some sense this is exactly the same change. There's nothing different has happened biologically in these 2 lineages. And in fact, There are just two different ways you could superpose them, and it's an arbitrary choice between them. And that's the position that Fred was taking in our arguments, and I finally came to realize it was absolutely correct. And that what you really needed to do was forget about the locations of the specimens relative to each other and just work with the differences between positions of landmarks. There's what's called a Helmert transformation. I don't have the map here, but basically it says you take the difference between the first coordinate and say the second coordinate. That's one of your data, the difference between an x coordinate between those two. Then you take the difference between, let's say, the average of the first two and the third. That's the second coordinate. Then you take the difference between the average of the first three and the fourth. That's the third coordinate. And you keep going like that. And if you have p landmarks, you'll have p minus 1 of those Helmert coordinates. And you do the same thing in the y-axis. You do the difference between the first two, then difference of the average of the first two, second, and so on. So this is actually one of the possible Helmert transforms. There's a family of them, but they'd all behave equivalently for our purposes. So you start with 2p coordinates, and you take these Helmert transforms. The important thing is you haven't lost any biological information by doing so. You've only lost the information about where you flop the fish down on the digitizer. And that's not biological information, that's you and your muscles and your psychology, not the fish. So you now have reduced yourself from 2p coordinates. And I should say I have here's just a slide saying that there's the superposition is in principle impossible. So what we're going to do is start out with that, start out with that transform of the data, and we go down from 2p coordinates down to 2p minus 2. Well, there's still one more problem, and that's rotation. How do you remove rotation? I'd love to tell you that there is another transform, a Helmert-like transform, that removes the rotations and brings the specimens into some space where rotation is not an issue. Alas, I don't know of any. If anybody knows of one, let me know. So I think what you as it just says here, the rotation doesn't have anything like a Helmert transform. So what do you get to do? Well, there are various ways you can choose your rotations. You can do a least squares superposition of the specimens and get the rotations from that. Notice that the superposition, the location part of the superposition, is not really information. There's also a thing called the Bookstein transformation, which is something, an approximate Procrustes-like, least squares-like thing that Fred invented. But what I'm suggesting is to go a little bit beyond both of those and to take the specimens. All of the data you're going to finally get is going to go into an analysis that's going to have likelihood as its framework, or it can just as easily have a Bayesian framework. Excuse me. But what you should do is take each specimen and rotate it, and then check what that does to the likelihood, and basically pick a maximum likelihood rotation for each specimen. So you choose the angles of rotation of specimens 2, 3 through n. I have it p here, but it's really n. To maximize the likelihood. You don't have to rotate the first specimen, because you can just take that as standard and rotate everybody relative to it. Because the whole collection of specimens, of course, can be rotated around without changing anything that is of interest. So we just take the first specimen in whatever position it is. And the result is you reduce the degrees of freedom for each specimen by 1 more by this maximum likelihood fitted rotation. And sorry, the slides are popping around again. Just a second. I have to get back to where I was. Okay. So we've come down from 2p coordinates to 2p minus 3, and that's where we're going to live. And the message after that is simply that all of the usual machinery of comparative methods then can be used from that point. We're going to treat the individual points as if they're moving by Brownian motion, but there is covariation between them. The interesting thing is what kinds of covariation? What do you see across the tree? So this issue of getting the right location and translation is not a trivial issue, but once you get rid of it, then you can just say, well, from here on in, let's approximate things by a Brownian motion model. There are other possible approaches, and we hope to explore those in the future. We're not going to be eliminating size, although in principle, if you want to eliminate size and just work with shape, we could explore ways of doing that. Let me show you a little bit of a computer simulation here. We'll show the operation. It says here the Bookstein transformation. It's actually not the Bookstein transformation we're going to use for Krusty's fitting. Here is a fearful species, the dreaded thresher salmon shark, Paleoncorhynchus, which is an imaginary species that we invented. And the reason we want to use this is because we're going to do funny things with the tops of the two fins. So it has to look something like a salmon and something like a shark, a thresher shark. And it's got 10 landmarks, the corners of the figure. This is the ultimate ancestor. And what I'm going to do is evolve on a phylogeny. Here is a tree, one of the true trees we've used in these simulations. The data that I'll show you is actually from a similar tree with 100 tips. So we're going to have 100 species. This is a true phylogeny generated by a pure birth process, a Yule process, and we produce a 100-tip tree like that. And when we do that, what we're going to do is assume that up that tree there are the following true unknown covariances. We're going to assume that each coordinate, here's the tip of the nose, moves in a circular Brownian motion. That is, in a Brownian motion with equal variance vertically and horizontally and no covariance between those two. And I'm just going to assume that for every coordinate around the fish, except for there's going to be some extra motion of the tops of the fins. There's going to be a vertical displacement that's of a somewhat greater variance, and there's going to be a diagonal displacement of the top of the tail with somewhat greater variance. And those two are going to be perfectly correlated. Those red movements are going to be perfectly correlated. So down in the lower part here, you see that. The circular motion plus this perfectly correlated linear red motion. That's the truth. We don't know the truth. Let's see if Brownian motion methods applied to this simulation can recover that. Here is a superposition. Now, this is getting a little silly. I just spent a lot of time trying to tell you there is no true superposition. Here's the true superposition. Here's what we simulated with it as if there were this superposition. The location information is actually not really there. And you can see the tops of the fins are moving a lot up and down, and the top of the tail fin is moving diagonally, and the other ones are just jittering around on this true tree. Now, if I don't have in our programs the maximum likelihood rotation machinery completely working yet. So what we've used here is the least squares per Krusty's fit, which isn't the perfect way of doing that. And now you'll see the specimens are pretty well superposed, and you'll see more motion of the top of the fins. Although you see some motion apparently of these landmarks of the constriction just before the tail, a little more than actually really happened. Well, what happens if we take these, excuse me, I'm sorry. If we take these fish specimens, we take the true tree, we make contrasts, use the ordinary contrast method, take contrasts and infer the covariances. What do we get? we're going to get covariance matrix, and it has eigenvalues and eigenvectors, and we can ask about the first principal component of the covariance matrix. Excuse me, I'm going to cough for a second. Tickly throat. Okay. And here's what we get. The first principal component of the variation is inferred to be this. It's got a little bit of motion. Now, this is the first principal component. So all of these movements are all perfectly correlated within that first principal component. Then there are other principal components. But the first one does in fact show vertical motion of the top of the fin and diagonal motion of the top of the tail, and a little bit of motion of the others, which really shouldn't be. They're rather too much near the tail, and that's because of the inefficiency of our rotation inferences, I think. So the short answer is not too bad. It's actually recovering the covariation that we put into the simulation. So things look good. The second part of the talk, I want to add another consideration, which is I want to talk about fossils. How do you deal with fossils? And in particular, there's a problem, and the problem is right now people take a molecular tree of some present-day species, and then they have a fossil form, and they make diagnoses based on synapomorphies as to which lineage the fossil might connect to, that it has to connect before this point, but after that point, for example. And then there's lots of people working on things like priors for how much earlier or how much later was the actual origin of that, the connection of that form with the rest of the tree. The approach I'm going to take here is different and doesn't use any diagnosis of synapomorphies. It's been explored by me, and it's independently invented by Fred Ronquist. And so he and I are going to both have independent but parallel papers shortly on this. And basically what we're doing, well, the method I'm using, which I think is very similar to the logic of Fred Ronquist's approach, is to say, well, we've got some molecular sequences, and they're neontological data, and here's a tree. But we also have morphology on those neontological specimens. We've also done our morphological analysis, perhaps morphometrics, on them. And we also have some paleontological data, some fossils. And we got morphology on them, but of course no molecular data. So the strategy will be this. We can take the present day morphology, and we can use comparative methods to infer covariation of characters. So we're using a Brownian motion framework. One could make more complicated Ornstein-Uhlenbeck processes, but let's leave that aside for the moment. And we can use the present-day specimens to infer the covariation among specimens on the tree, which we're, for the moment, going to assume is a known tree. Then we'll take the morphology of the fossils, using what we think we know about the covariation. We can place those fossils into the molecular tree. We can hook them in. And here is a sort of a little cartoon of the process. There are the white circles are the fossils, and the black circles are the present-day species. We can try various places of hooking them in, and using a Brownian motion model, we can, for each possible place that they could be hooked in, we can calculate a likelihood. I'll show you in a moment how. And you get a likelihood curve, and of course it favors a particular placement of the fossils. Now, the algebra of this is Brownian motion models. We're taking the tree as known, the tree for the present-day species as known, and we're taking, we're going to infer the covariation And what it turns out is that when you try a placement for the fossils and then you say, let's infer the covariation, let's figure out the likelihood of all of this. I'm not going to really go over the algebra here. But what you're going to get is that in the end, you come down to saying that the likelihood, I'll go down to the bottom of this panel here, the log likelihood for this particular placement of the fossils in the tree will be equal to some constants minus a constant minus the log of the empirical covariance matrix of the contrast. So you take the resulting tree, get the contrast, then you get the covariance matrix estimate from the contrast, and you take the log of its determinant. And it turns out that maximizing that likelihood by trying different placements of the fossils is equivalent to minimizing the determinant of the covariance matrix. And that's quite a nice result. It just says all we're trying to do is find the fossil placement that minimizes the determinant of our inference of the covariance among the characters. So that's basically what we're going to do. And this panel here in the projection shows you that. Here is a numerical example. Now it's a little, in a moment I'll tell you why it's a little bit fake. What I did was use a Yule process to make a truth tree. And then I took one of the lineages, which I chose lineage F for fossil, and shrank it back, erased part of it, get it back here. So it's going to be our fossil. And then I evolved 8 characters up this tree. The 8 characters actually had equal variances and no covariances, but we didn't tell the method that. The method's going to go off and try to infer the covariances and the variances, but we didn't tell them that are actually uncorrelated and equal variances, but that's okay. And then taking F and trying to hook it up in different parts of the tree and inferring the covariance matrix and taking the log of its determinant, or just the determinant is really enough. Here's what we get. Here is when F was actually found, so we're going to hook it to the tree somewhere below there. And what I'm showing you here are all the different places it could be hooked up. Here's where it really was hooked up. Here is the maximum likelihood estimate, right near my cursor, a little green arrow. The maximum likelihood estimate said as far up this branch as possible. It's the correct branch, but further up it. It would have gone further, but it wasn't allowed to because that's when we found the fossil. We can't have it connect after that. Down the tree and other possible placements, I've used traffic light colors here. So what you're seeing is green if you're within 1 unit of log likelihood, orange if you're within 2, and red if you're beyond that. And so it seems to want to place it. Oh, there we go, jumping all over the place. There we go. Yeah. It seems to want to place it in this region of the tree. So there is some signal there. And by the way, the inference of covariances among the characters was ballpark. It's not a huge amount of data. So you get, there sort of was not too much covariance, and the variances were roughly equal. So it wasn't bad performance. Now, if you're really thinking about this, you'll see that I pulled the wool over your eyes. I did something very, very fake in making this example. And what I did was I assumed somehow that we had a molecular tree on not a branch length scale, but a real time scale. I assumed that we somehow knew that this point on the tree is at that point in time. How could I possibly know that? And that brings up the very interesting issue of scaling of molecular trees, of calibration of molecular trees in chronological time. You can imagine hooking some fossils into a molecular tree by making some assumptions about how the branch length of the molecular tree relates to time, assuming some sort of conversion constant. And you can imagine comparing two different cases. Here on the left is one possible scaling. On the right is another scaling where the 1 unit of branch length is more time. And you can see that if you do that, you'll get somewhat different trees. And you can compare the likelihoods of those, or just use the determinant of the covariance, of the estimated covariance matrix. So I'm going to say that in addition to doing what I did in that simulation, you should actually stretch the molecular tree by different amounts, and for each of those, try the fossil in all possible places. And your best estimate overall of where the fossil goes and what the scaling of the molecular tree is that maximum likelihood or minimum determinant of the covariance matrix among those. And so it's an interesting approach. You could do it with multiple fossils. You could just try each fossil in all possible places. You can think of very easily of iterative approaches that keep reconsidering one fossil at a time until they all settle down, but also try different stretchings of the molecular tree, different scalings. So this has the interesting property of giving you a statistical assessment of where a fossil might connect, or where a set of fossils might connect, and also using a set of fossils who are collected at known times to make a scaling of a molecular tree. So it's a sort of integrated machinery for doing all of that. I hope to have this working in the contrast comparison, but it's a different program by Amelia Martin's contrast method in Philo sometime soon. I hope to get this in for publication sometime soon. Let's see. The third part of my talk is going to get a little closer to the issue of quantitative characters. I want to talk also about, in addition to continuous characters, which we've been using for these morphometric approaches and for these fossil approaches for fossil data, how do we handle morphological characters that are discrete? Everybody uses parsimony methods for these, although Paul Lewis has developed a method originally from Mark Pagel, in which you treat the two states of a discrete character as if they were nucleotides, and you use models very similar, simple stochastic process models on those, and those are becoming more popular, and to some extent providing some competition for parsimony approaches. But I want to suggest a different approach that I've been fiddling with the last few years. Here is the Pagel citation of Mark Pagel's and Paul Lewis's pioneering work on 0-1 characters and stochastic models of transition between states. I want to talk briefly about the threshold model, which was invented in 1934. It's a very old model now, so it's what would be 76, 77 years old, by a very famous guy, Sewell Wright, one of the three great founders of theoretical population genetics. Here's his picture in 1954 when he was inducted into the National Academy of Sciences and retired from the University of Chicago, moved to Madison. And he's holding the organism he worked with for many years, a guinea pig, and some of his equations are on the board. And there's a persistent rumor that what happened next is that after they finished shooting the picture, he absent-mindedly turned around and erased the board with the guinea pig. He was a famous absent-minded professor. Wright always furiously denied this, but there were people who had seen him lecture with guinea pigs as demonstration objects that said they had seen him do this. So maybe not on this occasion. The model he invented in 1934 for explaining a discrete character in guinea pigs, which was whether you had 3 or 4 toes on the hind foot. He actually had a third state, which was incomplete four-toedness, poor four-toedness. Well, what he did was to say, let's imagine there is a quantitative character probably polygenic quantitative character underlying, which you can't observe. We call that liability. It's come to be called liability in the quantitative genetics literature. And we have a threshold on the scale, and if you're one side of the threshold or the other, a developmental process results in either 3 toes or 4 toes, one of your 2 states. You can't see the underlying character. Well, it turns out that's a pretty good way of modeling. Here is a threshold model like that simulated on an imaginary phylogeny. What I've done is add the process of Brownian motion on the lineage and have the character start out at 0. We'll put the threshold at 0. It's arbitrary where it is. So initially, there is a population with 50% 3-toedness and 4-toedness. And then as it evolves up these lineages, the mean of the liability wanders. And as that happened, the fraction of 4-toedness and 3-toedness changes, and you get these results. I've shaded in these lineages according to the fraction of 4-toedness. And what we see is the means of the liability values, that you can't really observe those, but what you would actually observe is a fraction in each species, the fraction of 4-toedness and 3-toedness. And you can imagine that happening on multiple characters. And you can imagine the underlying liability scales covarying as they move up the tree. So it has some very attractive features, one of which is it has the feature that it allows for and incorporates in the model variation within species, phenotypic variation from individual to individual within species. It is a multivariate normal model, and because it's a multivariate normal model, it has covariances among everything and everything else, but there's only a limited number of parameters. If you have p characters, there's p times p plus 1 over 2 covariances, the diagonal and upper triangle of the covariance matrix. But if you were to go back into a sort of Pagel-Lewis 0-1 model and have p characters of that, and you try to come up with covariation terms, you'll see that there could be 2 to the p of those. It gets very messy, and it doesn't connect immediately to any quantitative genetics framework. So I'm going to go with this one and see what can be done. Now, I have a whole bunch of material, and we're running out of time. So let me just whiz through it. Here is the Brownian motion model on the liability scale and the thresholds of 2 characters, and an observation that we make of that in a particular lineage, the most common phenotype is 1-0. By the way, I'm going to back away from within species variation just for the sake of discussion and just talk about where the mode of the distribution is, what's the most common. But you can put the within species variation back in easily. The likelihoods that you would get will be integrals, shown down at the bottom here, integrals over the region, the unknown liability values, the unknown mean liability values in the different species. Those integrals are very, very hard to do. And you have the usual Brownian motion machinery with covariation. It's talked about in my book. It's talked about in other papers before that. And it turns out you can't really do the integration. It's far too difficult. There's no analytical solutions for it. And you have to end up doing MCMC. You have to do Markov chain Monte Carlo methods. And what we're going to try to do is not so much to compute the likelihood, but to infer the covariation across a bunch of 0-1 characters distributed on a tree. And to do that, we use the usual kinds of MCMC methods. We're going to use a variant of the algorithms, a well-known one called the Gibbs sampler. There's a picture of Josiah Willard Gibbs, who it was named after, famous pioneer of statistical mechanics. And we're also going to use the Metropolis Hastings method. We're going to update. We're going to have a tree we're going to fill in liability values, which we can't really observe. We have the phenotypes up at the top, but we're going to imaginarily fill in liability values, and then we're going to go around the tree updating those using a Gibbs sampler and our current estimates of the covariances and the Brownian motion machinery. And there's some analytical things you can do with that. And at the tips, we're going to update the liabilities using a Metropolis Hastings sampler in a straightforward way that I don't have time to go into. And basically, we can do this in multiple characters. We can update them in the tree. We can update our inference of the covariances. And we can end up with a rough, crude estimate of the covariances of the underlying liabilities. And let's see, I'm going to skip over all this stuff and just show you a little toy picture of this updating going on. Horizontal is the liability scale, vertical is time in the tree. Liabilities are being updated. Here's a computer simulation of a tree with 3 covariating characters over, I think it's 100 tips. And I've indicated by little red and white boxes how the zeros and ones came out in each species. The true covariances are these. There's 0 covariance between characters 1 and 3, positive between 1 and 2, negative between 2 and 3. When we infer, we do this MCMC. We do it over 100 different simulations of the character of the same tree. So these are 100 different cases. And on average, here are the true correlations. I've taken the covariances and turned them into correlations. Here are the true, the red arrows show the true correlations. The distributions show you the inferences. And the distributions, the estimates are roughly correct. But I think the thing you can immediately see is that 100 tips of these 3 characters is still not much of an information because the correlations are just very roughly inferred. They're the characters 1 and 2, where it should be 0.53, what we get is numbers going from below, slightly below 0 all the way up to nearly 1. And looking at that, you have to say, well, look, with all this machinery, you've managed to come up with an estimate, but it's a very rough estimate. And there, I think it brings up an important point. We can, by the way, extend this to take uncertainty in the tree into account by either using bootstrap samples of trees and doing this analysis on each one, or similarly Bayesian posterior samples of trees and do the analysis on each of these. And you can put within species variation into this and infer within species covariance matrices of the liabilities too, if you have samples of multiple individuals. And you can extend all this to Ornstein-Uhlenbeck. We haven't done it yet. Now, in the long run, these sorts of approaches, either the continuous character or discrete character, will be able to be connected to quantitative trait loci. But that's sort of off in the future, but at least the framework allows you to think about it. Maybe we could even use phylogenetic information to identify QTLs and see the distribution of QTLs, which loci were causing the variation changing across species. To do that, we would have to integrate within species information and between species information, quantitative genetic breeding analyses within species with phylogenetic data. But there's a couple of important points, and I'm going to end on this. We might even be able to get from that information about which of 2 correlated characters is actually under selection and which one's being taken along for the ride. But the final message, take-home message from this is you can use all these models. There's a glorious future ahead, but it's not that glorious because the estimates are terribly noisy. And you might say, well, we'll run more MCMC, and that'll subdue the variation and get very precise estimates. And what you'll find out is, no, that won't do it. What you need is more tips on the tree. But if you do that, you extend your data to bigger and bigger phylogenetic groups, to more and more different morphologies. And unfortunately, your models will start to break down. Your models are less and less likely to be valid as you extend off to more and more weird groups and include them in the analysis to get a larger sample size. So the take-home message is that we are not going to end up with precise estimates no matter how hard we try. And we're not ever going to be able to achieve a fly-on-the-wall view of evolution, which says we can tell exactly what happened at every moment. We're always going to have noise. And we're always going to have to learn ways of propagating that noise through the rest of our analysis and anything that we do with those data. So it's a little bit of a depressing picture, but if we don't understand that, we'll go promising people great precision in our grant proposals. And we have to be sensitive to, as you go up to more and bigger groups, that these simple Brownian motion type models are going to start breaking down. And we just have to be aware of that. So I'll just finish up by saying here's some references: Paul Lewis, Mark Pagel, Sewell Wright's paper on threshold models, Douglas Falconer wrote on that literature, and some papers by me on all of these issues going back to 1988. So this is the wonderful world of statistical non-molecular phylogenetics, and which we're using models that have been used by poultry breeders and in studies of guinea pigs. But the great advantage of it, it's one of the ways in which between species studies of molecular evolution and morphological evolution, and within species studies of things like quantitative genetics, are starting to come back together. And we're undergoing some sort of a grand reunion now of these long diverged lines of work that used to have very little to do with each other. Thank you for listening. I'll be happy to answer questions.